So the data, sample code, the slides are all up there. So for those of you in the back, if you have your computers, you might want to go ahead and pull it, or you can come up front, because we're going to try to do some live demos and hopefully it won't cut out. You guys hearing in the back?
You guys want to move up? You want? You can see the code better, see the slides a little better. Definitely move up. All right.
Okay, so I am here, my name is ryoko.kita, and I'm here from Capital One. I've been in New York for about 5 weeks, so I'm pretty new. My favorite things to talk about are coding and data science and math all in one. And so today I'm going to talk about Spark, and in particular Scala with Spark. You can also use Spark with R and Python and Java, but for some reason, I really like thinking in Scala, so I'm going to do Scala. Okay, so I'll start with who am I, because I sort of started. My background is mostly with hardware, so I used to work for Intel. And my last big manufacturing thing was helping them to get their server chips out. So the server chips that went on the market, I think about 2014, was my last product there. So I'm big on trying to understand computer hardware and how the software that we run as data scientists works on that computer hardware. So today, I'm hoping to help explain the code that you write and what's actually being executed so that you can get that performance gain when you use Spark. The other thing that I want to talk about is how to make it easier to work as a data scientist. So, coders are really good at Eclipse and they build and IntelliJ, whatever it is that they're using. They build, compile, build, do all that stuff, and then run their application jobs. And as data scientists, we tend to work a little bit more interactively with our data. So you're writing a function to create a new derived variable, and you want to see and make sure that that variable is getting derived correctly, right? Or that's getting computed correctly. So I'm going to show you something that I like to use called a Scala worksheet that helps me bridge that gap between something like easy Python, where you can see the output as you go, with Scala, which has a lot of functional programming stuff. So here are the topics. We're going to go through a little bit of hardware 101. I'm not sure where everyone is with their understanding of computer architecture, so we're going to do a very, very simple schematic, and we're going to try to keep it simple for the rest of the talk so that you can really start to think about the code on your hardware. We'll do just a standalone computer and then distributed systems. And then we'll talk about the software as well. So focus on why Spark. Why is that better than Hadoop MapReduce, for example? Better being, depending on your perspective. And then why Scala, say, over Python. And then I have a few demos that try to show the movement of the data as you're working with it on the hardware so that you can start to connect the Scala Spark commands with what's happening on hardware. And then I've prepared a very simple demo using some airline data that the government has. This data is pretty consistent, but it does actually need a little bit of transformation before you can use it. So we're going to talk a little bit about, as a data scientist working in a regular company, like Capital One, even if we have all of the data in the world, and even if we can buy whatever we want as far as augmenting data, there's still a lot of work that has to be done to cut the data before you can actually use it in your data models. And you'll probably find that out in the next 24 hours as you're working on your own projects. But it's a really big thing for data scientists that maybe don't get in school, that in that kind of real world scenario. So we're going to talk about it a little bit today. All right, so here's my picture of a very simple computer. I just want to go through the 3 key pieces and make sure we're all on the same page as far as what they do and what they can use. So let's take and use my little lime green box up here. This is what does all of your calculations. And I know it makes sense when I say it, and you probably know it in your head, But when people say, Spark is in memory. Well, Spark is sort of in memory, but the computation still happens on CPU, right? So it's the same for Spark and Hadoop. Anytime that the calculation is actually happening, it's all being done on the CPU. So that's not where the differentiator is between Spark and Hadoop. Actually, one more thing. If you guys have questions while we go, I'd rather take them as we're on the slide. So feel free to just pipe up and ask your questions. And I think that will be better for keeping the questions within the context of the topic. So don't be shy. I don't mind being interrupted. So just bust out with questions. All right. So then the memory part is what they call RAM, or you get the however many gigabytes on your phone or whatever that people talk about. So that's your temporary storage. There's a very fast connection from the CPU to the RAM. The data that you need to do the calculations, those calculations go much faster if you've got them in the RAM rather than the hard drive. So for example, from Intel, we make very fast connects to the RAM to try to make it so that our CPUs are running much faster. And most chip companies will work very hard on that connection. So Spark is working, when it says Spark works on memory, the reason why is because Spark is using the distributed memory across all the computers in the cluster to have the data on hand so that it can compute really quickly, right? So if the data is on hand, then it's going to seem like computations are happening much quicker, even if it's the same CPU chip. Now, Hadoop actually, in the HDFS, or distributed file system, actually works on the hard drive. And the hard drive is the thing that, I don't know how old you guys are, but it used to spin and kind of make the world, and if you got your computers back, just play with your hard drive. So now it's more solid state, but either way, that hard drive actually has to go through an input-output bus from your CPU, kind of the big light blue box. It has to go through another path all the way out. So when you're on Hadoop and you're trying to do a Hadoop MapReduce, it actually has to bring that data back into memory, and then the CPU does something to it, puts it back in memory, and then goes back out to the hard disk. And so that's the biggest differentiator between Hadoop and Spark, is where that data is.
So it looks like Spark won't scale up to the extent that it can, because...
Actually, it will, and we'll do that on the next slide. Good question, though. Anything else? Yeah.
So does Spark work in the same way that Redux or one of the database services that Facebook made report like Memcache, PHP, where it stores data on memory instead of 4 bytes per speed?
Yeah, so I'm not familiar.
Yeah, Redux.
Right.
Yeah, I'm not familiar with that, but if they ever talk about doing things in memory, then that's what they're talking about, the top blue box. And then your scaling question, let me get to that slide, and then can you ask it again? Because I want to make sure I understood the word scale correctly from your perspective. Okay, so that's one computer, right? So now when we go distributed, we've got a bunch of these computers, okay? And they all look the same, basically, more or less. The one big thing is that we've got our main kind of leader one, which a lot of people call the driver node. And there are a whole bunch of extra computers connected to that driver via actual cables. So like this kind of thing, right? And so, and those tend to be called the worker nodes. Now, the thing is, you can imagine that memory and CPU and hard drive on that central computer, if you have to go all the way through a cable.
That's what happens.
Okay. Okay. Yeah, stuff like that can happen. Right? So you have to be really thoughtful about whether you actually want to distribute your data or not. So the demos that I'm going to be showing today, I'm going to do on my laptop. Don't distribute. I mean, these files are only millions of rows. It's not very big. Just do it on your computer. If you've got billions, plus per second or whatever, yeah, you might want to go distribute. But you have to take into account that I/O and that movement of the data through the wires across look through your IO list to make it reasonable or a good ROI for you to start distributing your data. The other thing is with your CPU and the memory, so a bunch of things have to run on it, right? So the computer hardware by itself doesn't know how to distribute the data. It doesn't know how to manage the jobs that you're sending it to do, like calculate this. Well, it doesn't know how to calculate that and where all your data is unless there's some software running on it. So that's your Spark, that's your Hadoop manager, those Yarn, all those kinds of things that are managing your jobs. That actually has to run on computers as well. So that's going to take up some of your CPU, it's going to take up some of your memory. So you don't get all of the computer that you think you have. So that's another thing that you have to think about. And this is where the scale question comes in, right? So scale, it depends. It depends on what else is running on your system. It depends on how much of the data you're trying to operate on at once. And it depends on how big you've got your JVM set up and all of that kind of thing. So performance tuning is actually a lot of what goes on behind the scenes to make the models run. And it takes a lot of time because there are a lot of factors that you can adjust as far as how much memory is used for the caching, how big your result sets can be, how big your JVM memory can be. All of those things have to be tuned for your particular modeling system. All right, so it's a really good idea when you guys, I'm assuming you're still in school, but when you go out into the workforce and get a job, it's a really good idea to make friends with your server engineer because together you can do a lot more than if you're just trying to do something by yourself as a data scientist. Does that answer the scale question?
So what I meant is like, for any given server, the amount of RAM you have is a fraction of the amount of hardware space you have.
Right.
So like there are some data sets that are so huge that you just can't use what you have to do.
Great. Yep. So that's a good point. So the amount of data you're trying to operate on at once, if it's too big for your memory, on the workers, it'll do what we call spilling over. So it won't stop, but it'll start writing to the hard disk, and you'll see it plateau, and it'll take forever. And for me, forever is longer than my 20 minutes. So if it starts to take forever, then you really need to think about looking at the logic of what you're trying to do and see if you can start to either run the garbage collector, like your system, so this kind of thing, clear out the cache. You know, there are all those normal JVM types of things, yeah, that you also need to do. And that's where you really want to get your server engineer involved and, you know, possibly have a developer involved as well.
So one thing I'm hearing is it that if you can use the same programming model for Spark, but if you have too much data, then or if you're not tuning correctly, then you fall back to Hadoop platform.
Performance-wise, yeah.
Oh.
Yeah. Spark has this nice thing where, well, we'll talk about it, but you can do your state, well, let me just get it there. Just remind me. Okay, everybody okay with distributed? All right. So why Spark? Okay, this answers your question. So the cool thing is that the script that I'm going to show you, you know, we're going to run it on my local system. You can easily take the same flow of code and run it on a Hadoop system, running Spark, right? So you can run it distributed, you can run it local. There's just one little setting that you change, but the rest of the code is the same. So it's really nice because you can develop on a smaller data set in the privacy of your own computer before you go launch it. The other thing is you can do a lot of things all in one code flow. So you can bring in data from your hard drive, from a database, from Hive on HDFS. All of those are accessible. You can bring it into your Spark context. You can do your transformations using Scala, using all the functional programming that you can think of. Do your analysis, so Spark already has the machine learning models built in. You can use those. You can use anything that's Java or Scala based, that's open source library, bring those in. And then you can, once you get done, either transforming the data or you want to persist the model, you can also do that all within one script. So I like it because I don't actually have to do too much work managing the jobs and tasks, and this is a map and this is a reduce. Like I can do it all in one flow. and then Spark goes through and it does the analysis of your entire flow and decides whether, okay, these things need to go in serial format, these things can go in parallel, and it'll just start to execute. So it's really nice if you want to have the Spark manager do all of that optimization for you. And that's the launch, distribute, relaunch. So sometimes your jobs will fail. Spark will pick up on that and relaunch it for you. You don't actually have to do it. So, yes.
So it sounds like there's no reason, if this exists, there's no reason to use other jobs.
Some people like it. I guess I prefer this, so I don't ever MapReduce, do it with MapReduce. I'm not really sure why. I think some people just like it better.
It doesn't look like what we can do from that is build a primitive process data in batch as opposed to Spark does the online treating process.
So Spark has streaming, but you can do batch as well. And remember, like streaming is it can be pure streaming as you're doing one row at a time, but there aren't that many algorithms that you can update in a streaming mode. Most of them you're updating in at least a micro batch, right? So Spark has this cool thing where they call it a stream, but you can define the window of the stream. So it actually effectively becomes micro batches. So you can do that, you can do a full batch, whatever. I'm not sure about Hadoop if they have a streaming mode, but I think it's more batchy.
Have you ever tried Flink, and what do you think of the difference between Flink and Spark?
I haven't tried that. Yeah. Yep.
So what about for now, Spark is doing for the names Python, Java, and Scala.
Yep.
So do you foresee like other, languages implementing the Spark infrastructure?
I know so they recently added R since 1.4.
Ah, really?
Yeah, 1.6 just came out. So I think R integration is pretty well underway. So Spark is written with Scala Java. So that's where you get the entire functionality. And then PySpark comes a little bit later and starts to build the wrappers. And then R is even further back. There are some things like graphics, the graph analytics on Spark that you can only do in Scala. So I don't like to wait. I'd rather have my functions right away. So I work in Scala. Any other questions? These are really good questions. All right, so why Scala? Okay. As you can tell, I really like Scala. Functional program is what I call mind bending. It will send you loops in your brain and you'll need to take a break and have some chocolate. But it's actually, once you get good at it, it's amazing how much transformation of your data you can do with very short snippets of code. It's really, really nice. And just as a warning, once you get good at Scala, it's really hard to go back to something else. So just keep that in mind before you make the transformation. The cool thing about Scala functional programming is you're sending functions. You're not sending the actual data. So instead of sending a data structure that's a list with integers 1, 2, and 3, you define a list from 1 to 3, and that's what you send. And so it's much faster. The other thing is it does what's called lazy evaluation. So unless you actually are going to use that final bit transform data, you can tell it all the things that you're going to do to get it there, but it won't actually start the calculation until you need that first piece of data from that transform data set. So it's a good in a vacuum. It's good in that, it looks like it's compiling fine, but then it's bad when you actually try to take a piece of data set and you find out 10 steps ago you made a mistake. So we'll talk a little bit about debugging as well. I've already mentioned that GraphText is only available in Scala, and my favorite thing are Scala worksheets that I want to show you guys how to use. So moving on. So what we're going to work with today is airline data. I've put samples from mid last year onto that Git repo, just to make sure that you guys can run the same code. But it's a really nice website. So they've got prices up there. They've got all the departure landing times. It's an amazing data set if you guys are still looking for data to work on. It's relatively clean. Yeah, it's free. So we're going to look at that today. There is a little bit of formatting required. So for example, they store times as integers. So 9 o'clock became 900. There are some Java libraries that you can use to turn that into a time, but we're going to do it manually just so you can see an example function for room. Very simple function for room. And then, oh yeah, and I put the data. So for today, we're going to focus, because I'm really trying to show the connection between the software and hardware, we're going to do really simple things to the data just to keep it easy. But you can imagine taking that kind of beginning cleanup data prep and then going into, say, a logistic regression model or graphics or things like that. All right? Okay, so we're going to talk about functions that are applied per row and what that means on the hardware, and functions that require an aggregation of rows and what that means on the hardware. So stop me at any time if something doesn't make sense, because this core distinction will determine whether your stuff goes or not. There's a lot of code that will do similar things, and it will do them at very different speeds. And what I'm hoping that you guys take out of this talk today is to really think about what's happening under the covers so that you can actually make your stuff go and get to the result. Okay, so the first thing is we're going to talk about per row. And you'll see a lot of stuff out there, a lot of different images and things in Google that have a lot of arrows going every which way. I've tried to simplify it enough so that you can see the basics on the next 3 slides. If you need more information or you want to dive deeper, just ask and we'll go deeper into it. Okay. So on this one, what I'm trying to demonstrate is that we start with these rows of data that we've already put in memory, and we're going to apply a function on every row, and then we're going to write it back out to memory, and it's going to be a new row feedback. And as you can see, when you're applying a function on the row level, you can actually keep all of the data on each of the worker nodes and not have to move it very far. You're just going in and out. It's really fast. Okay? And Scala programming is really cool because applying that function to all the rows of data is usually just a one-liner. So you can do all of that in very simple code very quickly. And in this way, when you're creating new features, say like you're doing a tokenization or you're turning an integer into a time, for example, like all of those are very simple to do and they stand on a worker. So now, can you guys see that? Probably not. All right, so now why don't we take a quick segue into Scala worksheets. So I've got information up on at the end of the presentation in the appendix on how to download or install a version of Eclipse that has Scala built in. So there's Scala plugins for Eclipse, and I would encourage you possibly not to use those or maybe try them. When I last tried them, they didn't have the full functionality of Eclipse built with Scala, so I can go that route. I put the link for that in the appendix if you guys decide to try it. But the really nice thing about Eclipse built with Scala are these worksheets. So any file that has a .sc as the extension is a Scala worksheet. The files of the .scala are actual Scala files, so kind of like a .java. The .sc is set up with the regular imports. There are a few longer things, just so you can try the output. But then we go through the same setup that you normally go through with Spark, and setting up the Spark context and setting up the SQL context and things like that. And you see the stuff in the green on this side, on this right-hand side here. That's actually the worksheet is compiling your code and giving you the output right on that worksheet. So it's really nice, and you can see what it's doing. And I'll demo that for you once we get through a little bit of this. Okay, so the first thing we're going to do is we're going to load the data. This is using a Spark CSV module from Databricks. It's going to read my header, And it's gonna, the infer schema, what that does is it looks at each of your columns of data and says, oh, I think this is a string. I think this is an integer. And it'll go ahead and do that for you, which is really nice, because otherwise you have to tell it what it is. And then you can see the path to my data set. It's kind of long, because I've got it nested. The one thing about Scala worksheets is it thinks it's in the Eclipse working folder. So if your data and your code is there, then you can go straight to it. But I tend to import my files and keep the workplace separate. So that's why my file path is a lot longer. But just make sure you give it the full path and then we'll do that. The next few rows are output, actually, from that data load. So let's get rid of that. And then the example shows this. So that is what's called a user-defined function. It's basically a function that you define. And what we're going to do is I've just done some simple math. I had to go back and forth from string to float to string just to do some of the things that I wanted. But it's a good way to show you how you can chain functions all in one line of code. So the time integer is getting moved into a string. I'm dropping the right two characters, moving it back to string so that I can get it into a float, so that I can add it to some other stuff that I'm doing the calculations on. It's a lot of machinations, but I thought it was a good example of being able to chain functions, so I just left it like that. Then the next piece of code here is actually taking that data that we originally read in. It's going to create a new column with CRS step time x for float. It's going to apply that convert time user-defined function to that column CRS step time. And it does, so with that one command, it's going to take your data set, do all these calculations on your input column, and create a new column for you, just with that. And then this last one here is going to take the input field and the output field, and then take a sample of 5. So you can see that the integer 900 has now turned into a float 9.0. Okay, so to run this, you just save it, and it will start up, hopefully. If it doesn't start up, then you've done error somewhere. It should work. Okay, it's not going to do it for us today, even though it's just working. So we'll go back to the code. So, so basically, when you run it, it should give you all of the, you see kind of in the middle there lists this quarter is in it, month is in it, day is in it. So it'll go through and figure out your schema for you. And then that take 5 will actually make all of that upper stuff go. Because remember, it's lazy evaluation, and then it'll output just a full 5 for you. Okay? So that's per row, yeah.
So it says time.toString, then drop the right 2 characters, and then again 2String. Why do you need to? I'm just curious. Like, does it remain a string through that chain?
Yeah. When you drop the right 2, it turns into, when it's a 900, you end up dropping the 2 zeros and you end up with a 9, right? And Scala turns that into a character and not a string. And just for the ones up to 12 o'clock, you have to turn it back to a string. because you can't go from a character to a float, you have to go from a string to a float. So it's all these funny things. There's probably a much better way to do this, and I was just kind of showing how you can chain the functions. So that's a good question. And actually, I didn't catch that until at the very end when I was trying to take a sample, and it gave me an error, and I had to trace it all the way back up to that one particular problem. Okay, so now we're going to talk about the shuffle, the dreaded shuffle. So this is what Hadoop does. This is what Spark can also end up doing if you're not careful. And so you really have to control and know your code and know when it's doing the shuffle or not. So basically what's happening is you've got, bunches of original pieces of code in your memory. And you want your end function is taking an aggregate of all of the like rows. Okay. But to do that, depending on the aggregate function, you have to get all of your like rows in one place. Okay. To do that, it actually has to send the original data all the way back up to your driver. The driver has to shuffle it, send back the like rows to each of the workers, and then the worker can then do the aggregation. So that shuffle that the driver has to do with all this data movement is what takes a lot of time. There are some Spark operations that you'll explicitly be told, do not do this unless you absolutely have to. And you'll see lots of blog posts on it. This is what they're talking about, and this is why you don't have to do it. Sometimes you just have to, but what you want to do is get as much done as possible on each of your worker nodes as possible, and then run this function. The other thing is when you're reading data into your memory, you can do partitioning and shuffling in the beginning to try to get most of your data in one box that you can. So those are all optimization strategies that you'll read about if you get deeper into Spark. So here's an example. I won't try to run that again. And it's a little bit hard to see, but if you look at the top, it says select the airline ID, and then we're going to do make pairs out of it. So it'll be airline ID and then the number 1. So it's kind of classical map reduce, but we're just setting up what's called a pair RDB. So a big file with lots of pairs of airline IDs in one. And then when we do the group by, and we're mapping it out, we're going to take each of those airline IDs, try to collect all of the same airline IDs on the same box, and then add up all the ones to count per airline ID. As you can see here, it's taking 2 stages to do this on Spark, and here's the output. So the first number is the airline ID, and the second number is the count. Okay. So if you do a group by, anything that says group by in Spark, it's going to try to do this massive shuffle, right? Now, of course, you're already asking, can we do it any better? And there is a sort of shuffle. The sort of shuffle works only for certain types of operations. But what it does is it will take and do an aggregate first on the worker. So it'll aggregate the like ones, and then it'll send the data. So overall, it's sending less data, slightly faster. And the driver has to handle a little bit less data, so it probably won't crop out. And you won't notice it for smaller data sets, but you definitely will notice it for larger data sets. So this is also an option. And the command for that is the reduce by key. And there are actually a few more that you can start to think about. So if you see anything that's by partition, that's the same thing as each of your workers, so you can try that as well. The results are the same. The timing on this small data set of just millions of rows is very similar, but you can see it only takes 1 stage to do this operation. And then just for kicks, if you want to stay kind of in the SQL space of what we were doing before, there is a group by, but it is a group by. So it pretty prints, but other than that, you don't get anything from that. I just stuck that in there in case you guys want to play with it. Okay, so now we're coming up to the end. So hopefully you can see, maybe some good things that come out of using Scala, using Spark, and using them together. Thinking with your hardware in mind as you're writing software or your data science models. And then, you can take the airline analysis from here. So the code that I have on the repo does a lot of the transformations, and it started to looking at what kinds of metrics might be useful. So there's one that says late, as in the arrival time is after the stated time is supposed to be done. So that's one metric that you can define. Or you can say the overall time in the air was longer than it should have been. Or you can say, there are lots of ways of taking that data and making your own metric of what late means. So you might want to think about that. There are other tables in there, and I gave some examples of how to join the data together. So if you want to do it by get the month data in there, or if you want to get the actual name of the airline and do some text analytics, or if you want to do any other kind of transformation like that. There are a few sample tables in there that you can play with, and you can think about whether that will help you or not, or if it helps you to have it in the integer format, because some models only take integer inputs. So you can try it like that as well. And then other ideas are maybe you take months of data and start to do graph analytics and see, hey, where are the hubs per airline? So that might be an interesting analysis to do. Or is it better to try to go through a hub with this particular airline, or to take a different airline that goes through another hub that maybe has more on time? So all those kinds of questions you can start to think of with even this very simple data set. Yep.
So in the example you just showcased, we are always mapping the same function to each row simultaneously. I wonder if in Spark will be an optimized way, say, if I want to put something for each peer of different rows, I want to optimize that kind of calculations.
Yeah, so there what you would do is take the data set, filter for the rows that you want, and apply your function to that. And actually that's a really good use case, because say in your Scala script you've got take data set 1, filter out the B types, apply function B. Take data set 1, filter out the A types, apply function A, right? And you've got all of those lined up. Well, what Spark will do will say, oh, these aren't dependent on each other. I can run these all in parallel. And you'll see when it executes, it'll execute all of those functions all at the same time and manage pushing those out to the worker. So it's really fabulous that way. Even if you've got it written as a series, it'll parallelize it. So it's pretty cool. Any other questions? All right, I think that's the end. So I've got the appendix. I try to make as detailed as possible. For me, I was coming from Python into Scala, and I was like, what? Like, what do I type in where? And I couldn't figure it out. So with that in mind, I try to make these instructions as detailed as possible. If it doesn't work, I'm at ryoko.kita at capitalone.com. Feel free to email me. I'll try to help you through it. Just the one thing is, I only know how to work on Macs, so if you're on a PC, I'm really sorry. But if you're on a Mac, I can probably help you. And let me know if any of these instructions need to be improved, because I'm happy to go in and fix those. All right, great. Well, thank you.